3.3, the inverse of a quadratic function. So if you recall, the inverse of a function is just simply found by switching the x and y coordinates. So on a function, if you had the coordinate x and y, for your inverse function, the corresponding coordinate would just be the reverse, y, comma, x. And so we're going to be continuing to do that reversal here today with quadratic functions. So let's look at quadratic functions and finding their inverses. So the first one we're going to look at is f of x equals x squared, the parent function, the base function. Okay, so I'm going to start with graphing x squared. And it's useful to have some key points. So if you remember the points on y equals x squared, I'll just do a quick table of values. So here you have x and y, and let's pick -3, -2, -1, 0, 1, 2, and 3. And the y values, this is for y equals x squared. So -3 squared is 9, -2 squared is 4. Then we have 1, 0, and the numbers repeat 1, 4, and 9. So I'm going to plot these points on the graph. So here they are. And that, okay, and I'm going to connect my points with a smooth curve to show that I have a parabola. Okay, and so there it is. Label the graph y equals x squared. And there you have your function. Now, how do I find the inverse? We can simply take your coordinates for x and y from your original function and just reverse them. So for my inverse function, now I'll just write the coordinates like this. So x and y, -3 and 9 become positive 9 and -3. -2 and 4 becomes 4 and -2. -1 and 1 becomes 1 and -1. 0 and 0 doesn't change. 1 and 1, when you reverse them, doesn't change. 2 and 4 becomes 4 and 2, and then 3 and 9 becomes 9 and 3. And I can now plot these coordinates here in my grid to show you the inverse function. So here, 9 and -3 right there. 4 and -2 is right there. 1 and -1 is right there. 0 is 0. We're meeting our function here in the origin. 1 and 1, 4 and 2, and 9 and 3. And now I can connect these points with a curve to make this look like a kind of sideways parabola. All right, and there's my inverse function. And you might notice something interesting, and you may know this or not, or remember this. The inverse function is simply a mirror image of the parent function y equals f of x along the line y equals x squared. So, sorry, y equals x rather. So y equals x. So there's my symmetry line. Okay, so the function is a mirrored version of my inverse function, or vice versa. And I'm going to write here my inverse function notation right there. Okay. Now, how do I get this inverse function if I wasn't transforming coordinates like this? Well, you can reverse variables too. So if I did not have coordinates available, I could just reverse the variables inside my equations. So to do that, just simply follow these 4 steps. Step 1, make your f of x equal to y. So my function is y equals x squared. Step 2, reverse the variables. So now my y becomes an x, my x becomes a y. Okay, so x equals y squared. Step 3, reverse order of operations. So solve for reverse BEDMAS basically. So solve for y, or isolate for y. Okay, to do that, you take the square root of both sides. So square root of x equals y. But often when you take the square root of a number, you're going to get 2 answers, one positive, one negative, right? Because if you think about it, let's write here, the square root of 36, we know that's 6. But we also know -6 times -6 is 36. So 6 and -6 are 2 answers. Okay, and then step 4, use your inverse notation. So f inverse x equals plus or minus the square root of x. So you're just changing your y back to function notation by denoting it is the inverse function. Now, square root of x, you may recall square root of x is just a graph that looks like this part of my sideways parabola. So what's the negative square root of x? Well, it's the other half, this part. Now what's interesting about that is combined, this whole thing is not a function. It's just a relation. It does not pass the vertical line test. I put a vertical line made by this ruler. Oh, it's not going to pass. It hits that graph at 2 points. So it is not a function. Okay. Well, could you make it a function? So part C asks, well, let's go part B first. So let's state the domain and range. So domain and range, part B. Let's talk about function notation. Let's talk about the function. So domain and range. Domain, x is epsilon r. X is the element of all real numbers. We know that. Range, y is the element of all real numbers such that y has to be greater than or equal to 0 because there's no negative y values on the parent function. For the inverse function, however, well, domain and range is quite easy to do. If you know the domain and range of your function, all you have to do is switch them around. So my inverse function, the domain will be, will take on, well, the x variable is still the x variable, so x is the element of all real numbers, but the characteristics of your domain take from the characteristics of your range. So the whatever interval you have here for your range becomes the interval for your domain. So x is the element of all real numbers such that x is greater than or equal to 0. So of course you're not going to use the y, you're going to use x, but you're still using the same interval, greater than or equal to 0. Okay? So you look on the graph, the red graph, yes, it's great. X is a number that's greater than or equal to 0. What about the range? Same idea. You're still going to use the y variable for your range, but it takes on the characteristics or any intervals of your domain from your function. So if it's x is the element of all real numbers for the domain, then the range will be y is the element of all real numbers. Your graph continues on this way and this way. It will eventually reach an infinite number of y values above and below the x-axis. Okay, so now we can talk about how do I make this a function? Well, you could make it a function if you restricted the domain of the original function, right? So this is not a function. It doesn't pass the vertical line test, but you could make it a function. If I erase this left-hand part of my graph, then what would happen on this side, I would erase this negative part of my graph, and now it would be a function. So you could restrict the domain, right? I could say, make the domain of f of x, x is the element of all real numbers such that x is greater than or equal to 0. And then yes, it would be, your f of x would still be a function, and now your inverse would also be a function. All right, so let's look at another example. Given the quadratic, f of x equals 2 times x plus 3 squared minus 4. We're going to graph f of x and its inverse. Okay, so how do I graph f of x? We know this is a function in vertex form. So -3 and -4 is my vertex, so down here. Okay, how do I plot the rest of my graph? Well, I could do a table of values, and that would be fine too. If you are familiar with the step pattern formula, if a is equal to 2, then your step pattern would be, so 1a, 3a, 5a, so that's going to be 2, 6, and 10. And the way you use 2, 6, and 10 is you start from your vertex, you go over 1 to the right, and then up 2, because your step pattern starts with a 2. And from that point, you go over 1 and then up 6, because the step pattern says 6. And then you can continue going up over 1 to the right and then up 10, but there's no more room on my grid, so I'll just stop there. You mirror your points on the other side of the vertex, and then you connect your points with a smooth curve to show that you have a parabola. Okay, and so there it is. There's my f of x. Now what about my inverse? Okay, well, I could take my points on f of x, so I have the points now here. Let's just write them down. I have negative 5 and 4 going from left to right. I have negative 4 and negative 2. I have negative 3 and negative 4. And then I have negative 2 and negative 2. And then negative 1 and positive 4. Writing the inverse points, the reverse, just reverse your x and y. So the inverse would be 4 and negative 5, negative 2 and negative 4, negative 4 and negative 3, negative 2 and negative 2, and 4 and negative 1. And if I plot these points, I'll get my inverse function. So let's do that. 4 and negative 5, negative 2 and negative 4, negative 4 and negative 3, negative 2 and negative 2, and positive 4 and negative 1. And I connect these points with a smooth curve, I get my inverse function, which isn't actually a function, by the way. It's just a relation. It does not pass the vertical line test. Okay, so we graph them now. How do I get the equation? The same idea as before. You follow the 4 steps. So step number 1, replace your f of x with a y. So y equals 2 times x plus 3 squared minus 4. Step 2, you switch your x and y. So now I have x equals 2 times y plus 3 squared minus 4. Then the next step would be to reverse order of operations. In other words, you're going to be solving for y, just isolate for y. So you do that by, well, adding 4 to both sides. So x plus 4 equals 2 times y plus 3 squared. So that minus 4 on the right side is gone now. Next, if I divide both sides by 2, so x plus 4 divided by 2 eliminates the 2 on the right side, so I have y plus 3 squared. Now, if I take the square root of both sides, I will have square root of x plus 4 over 2 equals y plus 3 by itself on the right. But on the left side, make sure you show plus or minus, because you could get 2 results. And then finally, subtract 3 from both sides, so negative 3 plus or minus square root of x plus 4 over 2 equals y, and then replace your y with the inverse function notation. So the inverse function equals negative 3 plus or minus the square root of x plus 4 over 2. Okay, so again, now how can you make the inverse function a function? You can do it by restricting the domain of the original function. Okay, so how do we do that specifically now? Well, just like before, if I erase the left side of my original function, I can restrict the domain to say, hey, let's make the domain x is every real number such that x is only greater than or equal to negative 3. Negative 3 being that point where my vertex starts, okay? And then every value to the right of negative 3, that will count. Now, why am I doing that? Because by doing that, my original function will pass something called the horizontal line test. The horizontal line test, just like the vertical test, requires that if that horizontal line touches the graph at only one point, then you can rest assured that your inverse function will be a function and not just a relation. Why? Because if I restrict the domain now to x is greater than or equal to negative 3, what's happening? Well, this point does not exist anymore. This point does not exist. So that means this one will not exist, and this one will not exist. I can erase this part of my graph for my inverse. Let's just fix that. Okay, so there you go. This is my inverse. It is now a function because I restricted the domain of my original function, so that my inverse can now be a function and it can pass the vertical line test, because all the points that used to exist to make the other curve go downward do not exist anymore. Okay, what would change in your equation? So this equation would change just slightly. Inverse function would now be negative 3. Instead of plus or minus, you're only taking the plus portion, and now it's a function. Okay, Now, if you're given a word problem, what happens? Well, let's have a look. The rate of change in the surface area of a cell culture can be modeled by the function S of t. Okay, S of t is the rate of change of the surface area, and t is the time in hours. State the domain and range. Well, they already gave us the domain and is part of the modeling of the problem. So for part A, I can simply state the domain. The variable is now time. T is the element of all real numbers, such that t is a number between 0 and 12, including 0 and including 12. Now, the surface area of this cell culture changes with time. So now the corresponding range would be the surface area rate of change. So rate R is the range. I'm going to say S is my variable for surface area. That's the element of all real numbers. Now the surface area can't be negative, so we're going to be 0, starting with 0. And the upper point, well, think about what we have here, the vertex form, 0.18. If I locate that on an x, y axis, the vertex is at positive 6, somewhere here 6, and 0.18, 0.18, located in the first quadrant. Look at the a value, it's negative, so the graph is going to open down. Okay, now this picture will further reinforce that we can't go below the x-axis, otherwise we're going to get surface areas that are negative values, which don't make sense. So I have to restrict my range to be from 0 all the way to 0.18. So the other end of my interval will be 0.18, and that's my range. Okay. Determine the model that describes time in terms of the surface area. So now we want time in terms of the surface area. Okay, now how do we do that? It's not going to be the same like we've been doing with the other inverses. Okay, so I want you to note that in a real life context or in a word problem, to determine the inverse, you don't switch the variables. Let's make a note of that. Don't switch variables. Okay, instead, simply solve for the dependent variable. Okay, why? Because it's due to this cause and effect relationship between the two variables. So for example, when you're examining speed and stopping distance, the relationship between the two does not change. So you cannot just switch distance and velocity. It wouldn't make any sense. Okay, so don't just switch variables. Instead, just solve for the other variable. That's what you got to do for these word problems. Okay, so I'm going to take my equation. So S equals negative 0.005 t minus 6 squared plus 0.18, and I'm going to solve for t. Okay, so I do that by subtracting both sides by 0.18. So it's S minus 0.18 equals negative 0.005 t minus 6 squared. Okay, next I have to divide both sides by negative 0.005. So S minus 0.18 divided by negative 0.005 equals t minus 6 squared. Then if I take the square root of both sides, I get plus or minus the square root of S minus 0.18 over negative 0.005 equals t minus 6. And finally, if I add 6 to both sides, I will get 6 plus or minus the square root of S minus 0.18 divided by negative 0.005 equals t. And there's your inverse function to solve for t. Okay, what's the domain and range for this model? Well, you don't have to look at the function, just look at what you have in the domain and range for your original model. So let's write C over here. So the domain for the new model, for the inverse model rather, will just simply be the range of your original function. So domain will be SER such that 0 less than or equal to S less than or equal to 0.18. And the range will be TER such that 0 less than or equal to t less than or equal to 12. So not t is a number between 0 and 12. All right. Okay, one more example. Example number 4, this is from the textbook, page 161, number 9. So you're given a function 3x squared minus 6x. Determine the domain and range of f of x. So we're already given the domain. So the domain is quite simple. So domain, x is the element of all real numbers such that negative 2 less than or equal to x less than or equal to 3. So x is between negative 2 and 3, not including the endpoints. Now, how do I find the range? Okay, let's see. Well, maybe I should find the vertex first. How do I find the vertex? Well, you convert this to vertex form. That might help us a little bit. So if I convert this to vertex form, factor out a 3, x squared minus 2x. Then we complete the square. So we have x squared minus 2x plus 1. Minus 1 comes out as a minus 3. And then we factor, so we get x minus 1 squared minus 3. So what do we have? We have a vertex of 1 and negative 3. So negative 3 is a minimum. A value is positive, so it'll open up. Okay, so we're fine there. All right, let's look at the actual endpoints, negative 2 and positive 3. If I evaluate the function at negative 2, I would get 3 times negative 2 squared minus 6 times negative 2, which is equal to 24. Okay, if I evaluate the function at positive 3, I will get 3 times 3 squared minus 6 times 3, which is positive 9. So I can use these two y values to help me figure out the range, right? So we know f of negative 2 is bigger than f of 3. 24 is bigger than 9. So the range of f of x on this domain should be, range is y is the element of all real numbers such that negative, now remember, vertex lowest point is negative 3, right? That's going to help us with our negative with one of our endpoints. So negative 3 is the lowest y value. You can think of it visually. 1 and negative 3, that's your vertex. The graph opens up. So your y value has to be greater than negative 3. Okay, so y is between negative 3. And what's the highest value? Well, it's restricted on this side, the negative 2 side, right? That y value is going to be 24. So that's the highest it will go. So y is between negative 3 and 24. So when you're trying to figure out the range in a problem like this, look at what's happening at both endpoints, but you also have to find the vertex because those two endpoints may not end up being the vertex. You know, the vertex will either be a minimum or a maximum. So that will tell me what my minimum is because it's a parabola that opens up. And the maximum, well, you kind of have to figure that out from one of your endpoints. So the first endpoint is bigger, so that ends up being the other restriction. The 9 itself does not end up being used. Okay, part B, find the equation of the inverse if the original function is further restricted. Okay, so we saw in part A that the function has a minimum of negative 3 at x equals 1. And we know f of 3, so we know f of 3 is equal to 9. So that's going to help us. Okay, so if you restrict the domain of f of x, so now f of x, what's changing? It's going to be, so domain will be 1, x is between 1 and 3. Okay, so that's the new thing. So it's no longer starting at negative 2. So we don't care about that. We don't care about this 24 anymore. That's not going to really help us. So what's the range going to be restricted to then? Well, we know the vertex happens at 1. Okay, so the range, so what happens at x equals 1? We have negative 3. Okay, and so that range will be a value between negative 3 and what happens at x equals 3? Well, we have the y value of 9. So we know our range will be negative, y will be a value between negative 3 and positive 9, but not including negative 3 and 9 because we're not including 1 and 3 in the domain. Okay, so if we know that, then we know for the inverse, we just switch them around. So for the inverse, we can say -3 less than x less than 9. And for the range, we have y is element of all real numbers such that 1 is less than y less than 3. And so now we have established the domain and range for the inverse. Okay. Now, will that help us? Sure, maybe it'll help us. But really, let's look at now the equation itself. Okay, so what's the equation? 3x squared minus 6x. Now, here's why I found vertex form, because if I use the vertex form, it's pretty easy to rearrange this to find the inverse. Okay, because imagine f of x. So y equals 3x squared minus 6x. If you switched x and y, you would get x equals 3y squared minus 6y. That gets a little bit complicated to solve. To isolate for y again. Much easier if you just took the vertex form. So the vertex form is y equals 3 times x minus 1 squared minus 3. You switch the variables, x equals 3 times y minus 1 squared minus 3. And now we isolate for y. If I do this, take a little bit, we might need some extra room here. So if I add 3 to both sides, this is the solution here. X plus 3 equals 3y minus 1 squared. If I divide both sides by 3, I get x plus 3 over 3 equals y minus 1 squared. Take the square root of both sides, I get x plus 3 over 3 equals y minus 1. Plus or minus, remember it's a plus or minus square root. Now add 1 to both sides, so I get 1 plus or minus the square root of x plus 3 over 3 equals y. Okay, so there's my inverse function. Now, why did we not do the inverse function first? Because I wanted to show you something about the domain and range. So since the range, so we have the range here, right? Okay, so any value from this function, from this inverse function that has that turns out to be less than or equal to 1 are outside this range. So we kind of have to just note that. Just note that, right? So our inverse function, okay, 1 plus or minus the square root of x plus 3 over 3. That's our inverse function, but you just have to note that we are restricting the domain, right? So you can't just use this function for anything. We can't use the negative portion. It's going to be the positive only, simply because we are restricting the domain. The x has to be a number between -3 and 9. Okay, so yes, so you remove the minus sign. The reason why is because, yes, you can't have any y value less than 1. So you have a 1 here minus whatever this thing turns out to be, and this thing will always be a positive number. You can't have a negative as a result of the square root. This will always be a positive number. So 1 minus a positive number is going to be a number less than 1. So you can't have the minus. It's only going to be a plus. So 1 plus square root of x plus 3 over 3. And that's going to be your inverse function. Okay, so that's a little tiny detail, but it makes a big difference. And that's why it's important to look at your domain and range, even if the question is just asking you to find the equation. There's a reason why it's further restricted, so that's why you have to also find your domain and range. Okay, so that's quite a lot. There's some practice problems for you to do, but that is an overview of the inverse of quadratic functions. And that ends this video.